Welcome to this last lesson in the second part of this RHCSA video course. In this lesson we'll discuss how to work with logical volumes. We first discuss some of the benefits of working with LVM. Next you'll learn about the architecture, where physical volumes, volume groups and logical volumes work together to create an LVM-based storage solution. After setting up some logical volumes, you'll learn how the device mapper is used to provide a generic storage interface to work with LVM. In the final part of this lesson, you'll learn how to grow and reduce the size of LVM logical volumes and the file systems that are on it. As always, we conclude this lesson with a summary and a final exercise where you can practice the skills you need to have during the exam. So let's have a look why you would want to use LVM. First, it's a very flexible approach to working with storage. That means that volumes can consist of more than one disk, and it's easy to resize. You can make volumes bigger and you can make them smaller. Or if you have a failing disk, you can easily replace it with a new disk. And it also offers advanced options like working with snapshots, which allows you to make backups of files even if they are open. It is easy to add new volumes, and you can easily add many volumes as well. That is, with partitions you have a limit of a maximum of 15 partitions. In LVM logical volumes you can go all the way up to 256 logical volumes. Now let's have a look how to set up LVM. When working with LVM, you will always start with a physical storage device, such as a hard disk. In this example slide, I'm starting from a hard disk, which is SDA. If you are working from a hard disk, typically you would take a partition and mark the partition as a physical volume. The physical volume next goes into the volume group. And the volume group is really like the abstraction of all storage that is available. So that means when you create logical volumes, the logical volumes are created from the volume group. And from the logical volume perspective, you don't care about physical volumes that are sitting behind it. Once you have created a logical volume, you will get a device with the name dev vgroup logvol, or whatever you want to call it, and you do mkfs on that. So it's a logical volume that you are going to create a file system on. And from the volume group, if needed, you can add additional volumes as well, if there is space available. And if there is no space available, you can just add physical volumes to the volume group.
To create a logical volume, you start by creating a partition. So let's do fdisk on dev sdb again. As you can see, we have two partitions currently existing, and we have lots of space still available, about 800 megabytes. So I type n. To create a partition, I can do it as a primary partition. I make that partition number 3, and then I do first sector. I give it a size of 100 megabyte, and then I'm done. Now, to create partitions that you want to use in an LVM setup, there's something else that you need to do. You need to change the partition type. So I type T on partition number 3. I type L for an overview. And let's have a look if we see something that looks like a Linux LVM. There it is. So we need partition type 8E. Just verify that this is correct. And then I do W to write the changes, and parts probe to push the changes to the kernel. At this point I am ready to start creating my physical volume, my volume group and my logical volume. In this setup I want to start doing something easy to understand. So my partition, I'm going to use it as a physical volume. I'm going to create a volume group on top of that partition, and then I'm going to allocate all available disk space in the logical volume. So that would be pv create in the first step. Now pv create and all the other LVM related commands are very well documented. So I can recommend that you type pvcreate --help to get an overview of all the available options. As you can see here, there's just one required option to create a physical volume, and that is the physical volume itself. So let's do pvcreate on dev SDB3. And it tells me that dev SDB3 has been successfully created. I can verify that typing pvs, which is short for physical volumes. It shows me that I have a PV with the name SDB3. It's not in a VG yet. The format is LVM2. It has a P size of 100 megabyte and the same size that is available. So now I can put it in a volume group. So let's do VG create --help to see how that works. In this case there are two required options. I need to specify a volume group name and a physical device path. So VG create VG my VG dev SDB3. Now the volume group name is something that you can really choose for yourself, so anything goes, but I would highly recommend that you start the volume group name with VG. That makes it a lot easier to find the volume group at a later stage. So again, I can type VGS this time to see that I have my VG with one PV in it, no logical volumes yet, and a size of 96 megabytes. As you can see, 4 megabytes has been used for metadata. That is normal, and that's just the way it is. The next step is to create a logical volume in my volume group. Again, I'm doing LV create --help. As I know that I'm expecting lots of output, I pipe it directly to the LESS utility, which gives me an overview of all the options that are available. It still doesn't fit on the screen. The important thing, you can see it here, is a volume group name. So we need to specify a volume group name. We also need to specify a size. There are two ways to specify the size. You can count the number of extents, which is the building blocks that you are using, or you can just use uppercase L to specify a size in anything you like megabytes, gigabytes, terabytes, it all goes. These two are the required options. There's one more option that I would highly recommend, and that is -n. -n allows you to specify the name of the volume. That would be LV create -n LV my LV -L 96 megabytes. You remember, I still have only 96 megabytes left in the volume group. And VG my VG, that should do it. And as you can see, it does. Logical volume LV my LV has been created. So at this point I can use LVS to verify that it exists, and as it exists I can put a file system on it. Because this is a really small volume, I'm gonna use the ext2 file system. It's a really old file system, and the only reason I'm using it here is because it requires just a little bit of metadata. It doesn't do journaling, so it's very lightweight. So mkfs.ext2. Now the name of the LVM device is typically /dev/vg followed by the name of your volume group, so my VG, LV my LV. So the idea /dev/volume group name /logical volume name. We will see later that there are different ways of naming the LVM device as well, but for now this is good enough. You can see that the file system has now been created. Let's try and see if we can mount it. So mount /dev vg my vg lv my lv, and let's mount it on the /mnt directory, which is made for that purpose. So mount pipe and grep /dev shows me that the LVM volume has been mounted. You can see something weird here. So what I mounted was /dev/vg my vg /lv my lv, and what mount is returning is /dev/mapper/vg my vg /lv my lv. Does that matter? No, it doesn't, because both are symlinks to the real name of the device. I will show you. There we got it. You can see both are pointing to a device with the name DM3. DM3, that's a device mapper device, and that's the same device mapper that we have seen when creating LUX encrypted volumes.
When working with LVM, you need to be aware of the device mapper. So let me explain what the device mapper is. At the bottom we always have the kernel that takes care of things, of everything. But the kernel likes to work with abstraction layers. And really, device mapper is an abstraction layer that the kernel uses to communicate with certain types of storage devices. One of the storage devices that is using device mapper is a device that you've already seen. It's the LUX encrypted partitions that we've seen in the last lesson. LVM is also going to talk to the device mapper, which brings the benefit for the kernel, that the kernel just has to communicate with the device mapper and LVM and LUX and other systems like software RAID, for example, like multipath, for example. They all have to communicate with the device mapper directly. Now, talking about these abstraction layers in the kernel, now that we are at it, let me also mention VFS, which is the virtual file system. We have talked about the different file systems that exist on Linux, like ext4 and XFS, and well, that all goes through the VFS virtual file system layer. But that's not what matters here. What matters here is the device mapper in relation to LVM. Now, for you as an administrator, it is important what the consequences are. The consequences are really in the naming of the devices. From the device mapper perspective, you will get devices like /dev/dm-0 and dm-1 and dm-2. But you don't want to use them, especially not because these device names are created while your system boots and they can change. And that is why the device mapper also provides an alternative way of naming devices, which is the /dev/mapper directory. You have already seen the dev mapper directory while we were talking about LUX. Now, what we see in dev mapper is that LVM volumes get a name that has a structure of VG-LV. So all of your LVM logical volumes, you can find them in the dev mapper directory. And this volume name basically is just a symbolic link to one of these DM-anything devices. There's an alternative way for LVM naming as well, but this alternative way doesn't really relate to the device mapper. And that is the naming /dev/vg/LV. This is a name that comes from the LVM subsystem, and it also provides a symbolic link that goes to the same device mapper device. So in the end, the device mapper makes sure that you get your LVM devices and you get no less than 3 different ways of referring to a specific LVM device. And as an administrator, you should be aware that all 3 of these names basically all refer to the same device. Okay, let's talk about LVM resize operations. Resizing a file system sounds easy, but you need to be very aware of what you're doing. Otherwise, you will end up with a big mess, and that will be very difficult to fix. So in order to understand resize, let me just recap the LVM architecture. So on top we have the file system. The file system sits on a logical volume. The logical volume gets its available disk space from the VG, and the VG leans on physical volumes, which provides the actual disk space to it. Now imagine that your file system is running out of disk space and you want to make it bigger. So that means you want to extend the file system. In order to extend the file system, well, you cannot begin with the file system itself. You need available disk space in the logical volume. And in order to have the available disk space in the logical volume, well, you need possibly disk space in the volume group as well. So to make your file system bigger, it can happen that you need to start all the way from the physical volume. So first you need to create a new physical volume. Next, you need to assign the new physical volume to the volume group. Once it is in the volume group, you can grow the logical volume. And once you have grown the logical volume, you can extend the file system as well. So that's an extend operation. So the extend operation starts with the physical volume and goes all the way up. Now we also have the reduce operation, which means we want to make the file system smaller. Can you imagine what happens if you take the wrong order here? If, for example, you started by reducing the logical volume without reducing the file system first, it would mean that the file system would be bigger than the logical volume that sits below it. And the FSCK utility is going to see that there's a problem there, and it's probably going to mess up all your data. So if you are going to reduce, make sure to first reduce the file system. And once you have reduced the size of the file system, you can go on and reduce the size of the logical volume. And if you have done that, you can also reduce the size of the volume group and take away physical volumes you don't need anymore. So it's very important to really think about the order of resize operations. And in here you can see the order that you need to apply for any resize operation.
One of the benefits of LVM is that you can resize it easily. That is useful if your file system is running out of disk space and you want an easy way to make it bigger. So let's have a look at how that works. Typically it starts with df minus h. df is for disk free, minus h is for a human readable format. In here you can see that my LV that I just created still has 85 megabytes of available disk space. But if it would be full completely or almost completely, it's easy to make it bigger. If you want to make a file system bigger, you should consider the order in which to do it, because a file system sits on top of an LVM logical volume. Let's do LVS, and we can see that LV has a size of 96 megabytes. If you want to make it bigger, we need available size in the volume group. So let's have a look at VGS and see if disk space is available. So what we can see here is that the volume group has a size of 96 megabytes as well, and there's no free disk space available. That means that in order to make the file system bigger, we should work bottom up. So first we need to make the volume group bigger. And the only thing to do that is by adding a physical volume. So we'll be doing fdisk again. So fdisk dev sdb, and let's do p to see what we've got. As you can see, we have 3 partitions already, which means that there's room for one more. Now it might be possible that after creating this single partition that I'm going to add now, I need additional partitions. To make sure that I can add additional partitions at a later stage, I am going to create the partition that I'm going to add now as an extended partition, and within the extended partition I'm adding a logical partition, and the logical partition I'm going to use as a PV. First thing to do is n. As you can see, it tells me that there are 3 primary partitions and there's one only free, and that is exactly the reason why the system defaults to an extended partition. So I'm adding an extended partition. Extended partitions typically consume the rest of the remaining disk space. So I'm pressing enter for the first sector and enter for the last sector to take all the remaining disk space. We can confirm that by typing P, where you can see that the last sector that is used corresponds to the last sector on disk. Within the extended partition, I'm now going to add a logical partition, and I'm doing that by using N again. It tells me that all primary partitions are in use, and that is why it's automatically adding a logical partition. I press enter for the first sector, and I press 100 megabyte for the last sector again. And if I do P again, you can see that we now have an SDB5. Like before, we need to change the type of the partition, so I'm typing T for partition number 5, and I'm giving it 8E, which is the default for Linux LVM. I'm happy with everything right now, so I do W and part probe, and the partition should now know about the partition, so we can continue. In my previous demonstration, I have shown you how I first created a physical volume and then created a volume group. In this presentation, I want to take a shortcut. So we want to resize the volume group. Let's do VG tab tab and see if there is anything that looks like make the volume group bigger. You see it? We have VG extend. So I'm using VG extend -- help. VG extends needs a volume group and a physical device path. And the idea is that the entire physical device is added to the volume group. So I'm typing VG extend, VG myVG, followed by dev SDB5. And it doesn't really matter that SDB5 hasn't been marked as a physical volume yet, because VG extend will see it, and it will see that it meets all conditions to make it a physical volume, and it will automatically create it as a physical volume. If you do VGS now, you can see that the VG myVG has grown bigger, and there is 96 megabytes of available disk space. So at this point we can do LV something to make the logical volume bigger. Let's see if we have something that looks useful. Well, what about LV extend? So LV extend -- help to have a look at the parameters. There are different ways of making it bigger. It's the -L or the -uppercase L. So what you can see, you can specify an absolute number of extents to be added, but you can also specify something like a plus and a percentage of VG or of free or whatever. The solution I like a lot is LV extend -lowercase l plus 100% free. This just ensures me that all available disk space in the volume group is added. I also like -R, because -R, no matter what file system is used, is resizing the file system as well. You could do that differently by taking two different steps, which is first to make the logical volume bigger and then to make the file system bigger. But why do you want to do two different steps if you can all do it in one step as well? The next argument that we need is dev VG myVG LV myLV. And you can see that it is extending the logical volume to 192 megabyte, and it's automatically calling resize 2fs, which is the utility that resizes ext file systems. It sees that the file system is currently mounted on /mnt, and it is performing an online resizing action. And the result, if I do df-h again, you can see that right now I've got a 186 megabyte file system. You have just learned how to grow a file system. Growing a file system is a common task. Shrinking a file system is not so common. And even if you wanted to shrink a file system, you need a file system that supports a shrink. That is not the case for XFS, and that is why this shrinking operation I'm going to show you, we are doing it on ext4. Let's do a df-h. df-h shows that the dev mapper VG myVG LV myLV volume is mounted on /more data, and there is almost nothing used here. So that would be a perfect candidate to shrink the size of the file system and the underlying storage mechanism. Let's do a mount and see which file system is used. And we can see here that it's an ext4 file system, so that's good. This is something that we can make smaller. In order to do that, you must unmount the file system first. You cannot inline shrink a file system, so it must be unmounted first. So let's start by doing a U-mount on the /more data directory. Next, you need to consider the order in which you want to reduce the size of the file system. The first step would obviously be the file system itself, because if you start reducing the size of the logical volume and you haven't reduced the size of the file system first, well, then you will be in trouble. The next step would be to reduce the size of the logical volume, and depending on what you want to do with the size that has become available, you may have to do some other things as well. And after reducing the size of the logical volume, the storage has been given back to the volume group so that you can use it elsewhere. So in this demo, I'm just going to show you how you can reduce the size of the file system and how you can reduce the size of the logical volume. You remember man minus k resize is an excellent way to show all the different methods that are available to reduce file system size. So we have resize 2fs, which is the exe234 file system resizer. If I type resize 2fs help, it shows how it works. So basically it just wants the new size of the device. So resize 2fs dev vg my vg lv my lv, and I want it to have a size of 100 megabyte. I specify that as 100 M. It tells me that before reducing its size you need to do an E2 FSCK. This is a good idea because the E2 FSCK makes sure that the file system is consistent and that no problems are occurring on the file system. So let's just copy paste this command. So let's do E2 FSCK -F on the volume that we want to reduce. So that's okay. So at this point I can reduce the file system size to 100 megabyte. And it tells me that the file system is now 102,400 blocks long. Next step is to reduce the size of the volume. There's a nice command for that, and that is lv reduce. Let's do -- help as well to be sure about the right syntax that we're going to use. Looking at this syntax, you should consider what exactly you want to do. So we have 102,400 1 kilobyte blocks. So the basic measurement size that we've got here is kilobytes, and therefore it would be a good idea to use uppercase K for kilobytes as well. And that means that I'm going to do lv reduce minus uppercase L. I don't use a minus to take away, but I just redefine the size I want the volume to be. So that would be 102,400 K on dev VG, my VG, my LV. Now we see something really scary. This may destroy your data, file system and so on. Do you really want to reduce? Well, if you did good thinking, you can type yes, but if you made a mistake, well, you may run into big trouble. So make sure that you know what you're doing here. Now we can see that the logical volume LV my LV has been successfully resized. So if all is good, we should be able to mount it. I'm just using mount -A because it will find the file system as an unmounted file system in the FS step. And now if we do a df -H, we can see that the logical volume size has successfully been reduced. There's one thing I need to show you though, because this wasn't the easiest approach. I did like the approach because I wanted to be available of the two steps that are involved. You need to do something on the file system, you need to do something on the logical volume as well. But if you really want to do it in an efficient way, you can also use lv reduce with the -R option. Let me first unmount the more data directory so that I can show you. LV reduce minus minus help, and there we can see there's a -R option which resizes the file system. So LV reduce minus L, let's make it a 50 megabyte volume, -R on dev and VG my VG LV my LV, and up, there we go. So you can see the benefit of doing this. You don't have to do the E2 FSCK, and the LV reduce command is doing everything for you. You can see the FSCK is happening automatically, the resize operation is happening automatically, and the reducing of the logical volume is happening automatically. So if you really want to do it in an efficient way, better do it this way. There's one caveat though, and that is that you need support for the file system to reduce, and that is why -R won't work on all file systems. On some occasions you will have to use separate utilities anyway. So that's all. Your file system has now been reduced successfully.
Now let's do the exercise. It's a simple exercise this time, just 2 questions. First question, create a 1 gigabyte logical volume, format it with the XFS file system and mount it on /groups. Make sure the mount is permanent, so use fstab. And next I would like to grow the volume and its file system to its total size of 2 gigabytes.
First, let's create a 1 gigabyte LVM volume and give it an XFS file system. So creating an LVM volume starts by creating a partition. I will do that on dev SDB as in the previous exercise. Before creating any partition, type P to see what you currently have. We can see that I have an extended partition that consumes all the available disk space, so I need to work with logical partitions. So I do N and specify L to make it a logical partition. I accept the first sector and type +1 uppercase G to make it a 1 gigabyte partition. By default it is set of the type Linux. To make it LVM I need to give it the type Linux LVM, which is 8E. So I do T, give it a partition number 7, and I can enter the hexadecimal code directly. If I wanted to verify, then I can do an L first to show that 8E is the Linux LVM partition type. Let's verify this with P and W this to write it. It is telling me that rereading the partition table failed with error 16 device or resource busy. This is a pretty common error message when creating partitions, but you can fix it in most times by running the partprobe utility. And if that doesn't work, you will have to reboot. To check if it worked, have a look in proc partitions, and we can see that SDB7 is existing right now. So at this moment I can create the LVM volume. Of course we can go for the PV create, VG create, LV create, but if you do VG create you can specify the device immediately. That is VG create VG disk, followed by the name of the partition, dev SDB7. It creates a physical volume as well as the volume group. So now we can do LV create to make the logical volume. Let's do ---- help first to get an overview of all the available parameters. You can see it is quite a lot. It doesn't even fit on one screen, but most of the parameters are optional. What isn't optional is that we need to use -lowercase l or uppercase L to specify a size. We also need to specify a volume group name, and it is useful to specify a name as well. If you don't specify a name, you'll get the logical volume with a name like log vol00, and that's not very easy to recognize later. So LV create minus L1G minus N LV disk. Yeah, and we are using a VG disk as the underlying volume group. And now look at that, it tells me that it has insufficient free space, 255 extents, and it requires 256 extents. That means that of the 1 gigabyte that I allocated to the partition, some space has been used for metadata. The easiest way to get out of here is to change minus L into minus L 100% free. That allows it to use all available disk space. So if we do an LVS, we can see that now we have an LV disk with a size of 1020 megabytes. Next we need to make an XFS file system on it. And of course we are doing that on dev VG disk, LV and disk. So this gives me the summary, and let's see if we can mount it. So mount dev VG disk, LV disk on /group, and that apparently works. I'll do a mount pipe grab group, and we find out that on the last line the LVM volume has been mounted successfully. Now I need to grow it, the volume as well as its file system. Let's start by creating a partition again. New partition, make it a logical partition. Enter to accept, to use all the space that's left. T for the partition type, partition number 8, and the hex code will be 8E. P to get an overview, looks good. So let's do W followed by part probe to push the new partition to the kernel partition table as well. Oh, by the way, I use part probe without any arguments, so it's trying to push the partitions on the CD-ROM as well to the partition table, and that obviously is not going to work. So we need a VG extend -- help to make it bigger, and in order to do that, a VG extend, a VG disk dev SDB8 would do the job. So the physical volume has successfully been added. If you type VGS, you can see that we now have VG disk that consists of 2 physical volumes. Next we need LV extend to grow the partition as well. Now LV extend has an option to specify the size, and I like minus L a lot because you can use something like plus 100% free. It also has a very useful minus R, which is resize FS. This will resize the file system automatically for you. So LV extend minus L plus 100% free minus R to resize the file system, dev VG disk LV disk. And you can see here that everything is happening. So it has been extending the logical volume to 2 gigabytes approximately, and it has resized the file system, what we can see here. So if we do a df -h, we can see that we now have a 2 gigabyte volume that is mounted on group, and that is what was asked in the exercise.
This brings us to the end of this lesson. In this lesson you have learned how to set up an LVM storage infrastructure. Working with LVM is definitely important on Red Hat because it makes your storage allocation flexible. So be prepared to answer any question related to LVM topics we have seen in this lesson on the exam.